Smallpox. Smallpox is the only human disease ever eradicated, officially eliminated in 1980 after a massive global vaccination campaign. The virus killed an estimated 300 million people in the 20th century alone, with a fatality rate of about 30%. Survivors were often left blind or severely scarred. It was a horrific disease that humanity fought for centuries. And then, we won. The last natural case occurred in 1977 in Somalia. By 1980, the World Health Organization declared smallpox eradicated from nature. So, why does smallpox still exist? Because we kept it. After eradication, the WHO ordered all countries to destroy their smallpox samples or send them to 2 designated maximum security facilities: the Centers for Disease Control and Prevention, CDC, in Atlanta, Georgia, and the State Research Center of Virology and Biotechnology, Vector, in Koltsovo, Russia. These are the only 2 places on Earth officially authorized to store live smallpox virus. The justification for keeping smallpox is research. Scientists argue they need samples to develop better vaccines, to study the virus in case it reemerges, and to develop treatments for potential bioterrorism attacks. But many experts believe the risks far outweigh the benefits. The WHO has repeatedly debated destroying all remaining samples, but the US and Russia have consistently opposed complete destruction. Here's what makes smallpox so dangerous if it were released. No one under the age of 45 is vaccinated anymore. Routine smallpox vaccination ended in the 1970s once eradication was achieved. This means the vast majority of the global population has zero immunity. If smallpox escaped from a lab or was deliberately released, it would spread through a completely susceptible population. The virus is highly contagious, spreading through respiratory droplets and direct contact. An infected person can transmit the virus before symptoms appear, meaning it could spread globally before anyone realized what was happening. Modern air travel would allow smallpox to reach every continent within days. Mathematical models suggest that a smallpox release could infect hundreds of millions of people, killing 30% of them, potentially 100 million deaths or more. The security around smallpox storage is supposed to be absolute. Both facilities are BSL-4, Biosafety Level 4, the highest security classification. Scientists work in positive pressure suits with their own air supply. Multiple containment barriers exist. Access is severely restricted. Inventory is carefully tracked. But accidents happen. In 2014, FDA employees cleaning out an old storage room at a CDC facility in Maryland found 6 vials of smallpox in a cardboard box. The vials had been sitting there, forgotten, for decades. They were in an area that wasn't even designated for storing dangerous pathogens. The vials were intact and the virus was still viable. If someone had accidentally broken a vial, smallpox could have been released into an uncontrolled environment. In 2021, a laboratory worker at a Merck facility in Pennsylvania found frozen vials labeled smallpox in a freezer. The FBI and CDC were called. The vials were tested and fortunately did not contain actual smallpox. They contained vaccinia virus, used in smallpox vaccines. But the incident highlighted that labs don't always know what's in storage, and dangerous pathogens can be mislabeled or forgotten. The existence of smallpox in labs creates other risks. What if a rogue scientist stole a sample? What if Russian or American security failed and the virus was taken? What if a facility was damaged by natural disaster or war? What if an employee was bribed or coerced? Smallpox is the only disease we've ever completely eradicated, and we're keeping it alive in freezers. Every day those samples exist is a day humanity risks the return of one of its worst killers. 1918 Spanish flu. The 1918 Spanish flu killed an estimated 100 million people worldwide, more than World War I. It infected 1/3 of the global population and had unusual characteristics. Instead of mainly killing the very young and very old like typical flu, it killed healthy young adults at high rates. The virus disappeared after the pandemic ended, and for decades it was just a historical horror. Then, in 2005, scientists did something controversial. They recreated it. Researchers from the CDC and other institutions reconstructed the 1918 flu virus from genetic material recovered from victims' bodies. some preserved in Alaskan permafrost, others in tissue samples. They published the complete genetic sequence and successfully synthesized a living version of the virus. The stated purpose was research. Understanding what made the 1918 flu so deadly could help prepare for future pandemics. The recreated 1918 flu is stored at the CDC in Atlanta in BSL-3 enhanced and BSL-4 facilities. Experiments with the virus showed it was extraordinarily virulent. When tested on mice, the 1918 flu killed 100% of infected animals. When tested on monkeys, it caused rapid and severe illness. The virus replicates faster and spreads more efficiently than modern seasonal flu strains. Many scientists question the wisdom of recreating this virus. In 2005, articles in major science journals asked, "Is this really a good idea?" The concern was twofold. First, the recreation showed that synthesizing deadly viruses from published genetic sequences was possible, potentially providing a roadmap for bioterrorists. Second, it created a sample of an extinct civilization-ending pathogen that now exists in a lab and could potentially escape. The 1918 flu is particularly dangerous because it's a novel strain. While seasonal flu circulates constantly and people have partial immunity from previous infections and vaccines, the 1918 strain is completely new to modern immune systems. If released, it would behave like a pandemic flu, spreading rapidly through a susceptible population. Modern medicine would help. We have better treatments, ventilators, antibiotics for secondary infections, and could potentially develop vaccines. But the 1918 flu spread incredibly fast. It went from the first cases in March 1918 to worldwide pandemic by fall. With modern air travel, it would spread even faster today. Before vaccines could be produced and distributed, millions could die. The reconstruction of the 1918 flu set a precedent. If scientists could recreate one extinct pandemic virus, they could recreate others. In 2017, researchers published a paper showing how to synthesize horsepox, a relative of smallpox, using mail-order DNA and about $100,000. The implications were clear. The technology exists to recreate any virus whose genome has been sequenced and published. The 1918 flu exists in labs right now because scientists made a deliberate decision to bring it back. It was extinct. We were safe from it. And then we recreated it for research. The samples are stored under high security, but they exist. And unlike naturally circulating pathogens, this virus has no right to exist. We chose to make it real again. Ebola Zaire. Ebola Zaire is the deadliest of the Ebola virus species, with fatality rates ranging from 60% to 90%, depending on the outbreak and available medical care. The virus causes hemorrhagic fever. Victims experience internal and external bleeding, organ failure, and often die within days of symptom onset. It's a horrific way to die, and Ebola outbreaks terrorize affected communities. The 2014-2016 West Africa Ebola outbreak killed over 11,000 people and showed how devastating Ebola could be when it reached urban areas. Previous outbreaks had been contained partly because they occurred in remote villages, but in 2014, Ebola reached cities with international airports. Cases appeared in the United States and Europe when infected travelers arrived from West Africa. The outbreak sparked global panic and required massive international intervention to contain. Ebola. Zaire samples are stored at BSL-4 facilities around the world, including the CDC in Atlanta, USAMRIID, US. Army Medical Research Institute of Infectious Diseases at Fort Detrick in Maryland, the National Institutes of Health, Public Health England, and other facilities in Canada, Germany, France, and elsewhere. These labs study Ebola to develop vaccines and treatments. Research on Ebola has led to important breakthroughs. The RVSV-Zeboavi vaccine, developed through research using live Ebola virus, proved effective during the 2014-2016 outbreak and has been used in subsequent outbreaks. Treatments like monoclonal antibodies have also been developed through research using live virus. This is the argument for keeping Ebola in labs. We need it to develop countermeasures. But Ebola in labs creates risks. In 2004, a Russian scientist working at Vector died after accidentally sticking herself with a needle containing Ebola. She developed hemorrhagic fever and died despite treatment. Her death showed that even in maximum security labs with trained personnel, accidents happen. If Ebola escaped from a lab into a major city, the consequences could be catastrophic. While Ebola requires direct contact with bodily fluids, it doesn't spread through air like flu. It spreads quickly in conditions where people care for sick family members or during burial practices. In hospital settings, without proper protective equipment, healthcare workers become infected at high rates, as happened in West Africa. The virus is extraordinarily deadly. Even with modern intensive care, mortality rates are high. During the 2014 outbreak, patients treated in advanced medical facilities in the US and Europe had better survival rates, but still face 30–40% mortality. In resource-limited settings, mortality exceeded 70%. If Ebola spread in a major city before containment measures were implemented, thousands could die. What makes Ebola particularly nightmare-inducing is the possibility of mutations. Current Ebola strains spread through direct contact, but viruses mutate. In lab experiments, researchers have made Ebola more transmissible in animals. A 2012 study showed that Ebola could spread through respiratory droplets between pigs and primates under laboratory conditions. If a mutation made Ebola airborne in humans, it would be apocalyptic, an airborne virus with 70% plus fatality rates. Ebola exists in multiple labs, each a potential point of failure. More facilities mean more risk. And research on Ebola sometimes involves manipulating the virus, making it more transmissible or virulent in animals to study pathogenesis. These experiments create risks that the modified viruses could escape. Marburg virus. Marburg virus is Ebola's equally deadly cousin. Like Ebola, it causes hemorrhagic fever with fatality rates ranging from 23% to 90%, depending on the outbreak. The virus first appeared in 1967 when laboratory workers in Marburg, Germany, hence the name, and Belgrade, Yugoslavia, became infected while working with tissues from African green monkeys imported from Uganda. 7 people died in that outbreak. Since then, Marburg has caused sporadic outbreaks in Africa, most notably a 2004-2005 outbreak in Angola that killed 90% of infected individuals, the highest fatality rate ever recorded for any hemorrhagic fever outbreak. Most victims died within days of symptom onset. The virus spread through hospitals and families caring for the sick. Marburg samples are stored at the same BSL-4 facilities that store Ebola. The CDC, USAMRIID, NIH, and several international research centers. The virus is studied for vaccine development and to understand hemorrhagic fever pathogenesis. Research has produced experimental vaccines that show promise in animal studies, but no approved human vaccine exists yet. The security concerns with Marburg are similar to Ebola, but with an additional worry. Marburg has been weaponized. During the Cold War, the Soviet Union's biological weapons program, biopreparat, weaponized Marburg virus. They produced it in large quantities and developed delivery systems. After the Soviet Union collapsed, information about the program was revealed, raising concerns about whether all samples were destroyed or if some might have ended up in unauthorized hands. Ken Alibek, a defector from the Soviet bioweapons program, wrote in his book Biohazard that the Soviets had successfully weaponized Marburg and tested delivery systems. The program was officially ended in the early 1990s, and facilities were supposed to be dismantled. But questions remain about whether all dangerous materials were accounted for. If Marburg escaped from a modern research facility, the outbreak would mirror Ebola, rapid spread through direct contact, high mortality, terror in affected communities, and potential for international spread through air travel. The 90% fatality rate seen in the Angola outbreak makes Marburg potentially even more deadly than most Ebola strains. The virus's history as a bioweapon makes it particularly concerning. The Soviets chose Marburg for weaponization, partly because of its extreme lethality and partly because no vaccine or treatment existed. Even today, treatment is supportive care only. There's no specific antiviral. A deliberate release would be devastating. Marburg is also concerning because it occasionally emerges naturally. The virus's natural reservoir is the Egyptian fruit bat, and people can become infected through contact with bats or mines where bats live. This means new outbreaks can occur, providing opportunities for the virus to mutate or adapt. Studying the virus in labs is important for pandemic preparedness, but it also means keeping one of the world's deadliest pathogens in storage where accidents could happen. Nipah virus. Nipah virus emerged in Malaysia in 1998, causing an outbreak that killed 105 people and led to the culling of over 1 million pigs. The virus jumped from fruit bats to pigs to humans. Infected people developed encephalitis, brain inflammation, with fatality rates of 40 to 75%. There is no vaccine and no specific treatment. Since the initial outbreak, Nipah has caused regular outbreaks in Bangladesh and India. These outbreaks are terrifying. The virus spreads from person to person, has high mortality rates, and survivors often suffer permanent neurological damage. The 2018 outbreak in Kerala, India, killed 17 of 19 infected individuals, a 90% fatality rate. What makes Nipah particularly concerning is its pandemic potential. Studies have shown that the virus can spread through respiratory droplets, meaning it could potentially cause an airborne pandemic. During outbreaks in Bangladesh, person-to-person transmission occurred, including transmission from patients to healthcare workers. The virus can also spread through contaminated food, particularly date palm sap, contaminated by infected bats. Nipah samples are stored at multiple BSL-4 facilities, including the CDC, CSIRO Australian Animal Health Laboratory, and several research centers in Asia. Scientists study the virus to develop vaccines and treatments and to understand its transmission dynamics. In 2011, the film Contagion used a fictional virus based on Nipah as its pandemic pathogen, highlighting the virus's pandemic potential. The film's scientific consultants chose Nipah-like characteristics because they represented a realistic worst-case scenario: high mortality, respiratory transmission, rapid spread, no vaccine or treatment. Research on Nipah has shown disturbing findings. Studies demonstrate that the virus can infect a wide range of mammals and can sometimes transmit through the air between animals. In 2012, researchers showed that ferrets, often used as models for human respiratory diseases, could transmit Nipah through respiratory droplets. This raised concerns that the virus might be capable of efficient human-to-human airborne transmission if certain mutations occurred. If Nipah escaped from a lab, particularly a strain that had been made more transmissible through research, the consequences could be catastrophic. An airborne virus with 50–90% fatality rates would cause global panic. Unlike Ebola, which requires direct contact with bodily fluids, an airborne Nipah virus would spread like influenza, potentially reaching every country within weeks. The virus's natural emergence pattern, jumping from bats to intermediate hosts to humans, means new outbreaks will occur naturally. But the lab-stored samples represent concentrated risk. They're studied specifically because they're so dangerous, and that danger is what makes their storage so concerning. Lassa fever virus. Lassa fever is endemic in West Africa, causing an estimated 100,000–300,000 infections and 5,000 deaths annually. Most cases are mild or asymptomatic, but severe cases involve hemorrhagic symptoms, organ failure, and death. The fatality rate in severe cases is about 15–20%, but can be much higher in certain populations, particularly pregnant women. Mortality rates above 80% in third trimester. The virus is spread primarily through contact with the urine or feces of infected mastomys rats, which are common in West African homes. Person-to-person transmission occurs through direct contact with infected bodily fluids. Healthcare workers are at high risk, and nosocomial, hospital-acquired outbreaks are common in West Africa. Lassa fever samples are stored at BSL-4 facilities, including the CDC, USAMRIID, Bernhard Nocht Institute in Germany, and several African research centers. Research focuses on vaccine development. Several promising candidates are in development, and improving diagnostic tests and treatments. What makes Lassa concerning as a pandemic threat is its prevalence and potential for spread. Unlike rare viruses like Ebola or Marburg that cause occasional outbreaks, Lassa infects hundreds of thousands of people every year. This means the virus has constant opportunities to mutate and adapt. If mutations increased its transmissibility or virulence, a localized West African disease could become a global threat. Cases have been exported internationally. Travelers returning from West Africa have brought Lassa to the United States, United Kingdom, Germany, and other countries. Most imported cases have been contained, but they demonstrate that the virus can reach anywhere through air travel. In 2020, Germany experienced a Lassa fever scare when a medical student who had volunteered in West Africa returned home and died from the disease. Several healthcare workers who treated the patient were exposed and monitored. The incident showed how easily hemorrhagic fever viruses can spread internationally and how difficult they are to contain even in advanced healthcare systems. Research on Lassa virus has involved controversial experiments. Scientists have studied how the virus might become more transmissible and what genetic changes would make it deadlier. While this research aims to predict and prevent pandemic strains, it also creates those very strains in the lab. If these modified viruses escaped, they could be more dangerous than naturally circulating Lassa strains. The sheer number of facilities storing Lassa increases the risk. Because the virus is endemic in West Africa and relatively common compared to Ebola or Marburg, more labs keep samples for research. Each facility is a potential point of release. And because Lassa causes milder symptoms in many people, someone infected in a lab accident might not realize they were sick until they had already exposed others. Engineered H5N1 bird flu. In 2011, two research teams did something that sparked international controversy. They engineered H5N1 avian influenza to be transmissible between mammals through respiratory droplets. Natural H5N1 doesn't spread easily between humans. It mainly infects birds, and humans get infected through close contact with infected poultry. But the engineered strains could spread through the air between ferrets, the animal model for human influenza, meaning they could potentially cause an airborne human pandemic. The research was conducted by teams led by Ron Fouchier in the Netherlands and Yoshihiro Kawaoka in Wisconsin. Both teams made genetic modifications to H5N1, creating strains that could transmit through respiratory droplets. When they tried to publish their findings, the U.S. government initially tried to prevent publication, arguing that the research was essentially creating a bioweapon and publishing a recipe that terrorists could follow. After extensive debate, the papers were eventually published in 2012, though with some details omitted. The researchers argued that the work was important to understand how pandemic flu strains emerge and to prepare surveillance systems to detect dangerous mutations in nature before they cause pandemics. Here's why this is terrifying. H5N1 has a 50-60% fatality rate in humans. Most flu pandemics have fatality rates of 0.1% to 2%. The 1918 Spanish flu, which killed 50 of 100 million people, had a fatality rate around 2-3%. An airborne flu virus with 50% fatality would be apocalyptic. If the engineered H5N1 escaped from a lab and spread like seasonal flu, it could kill billions of people. The engineered strains are stored at the labs where they were created, Erasmus MC in Rotterdam and the University of Wisconsin-Madison, as well as possibly at other facilities they've been shared with for research. They're kept under BSL-3 enhanced conditions, which is high security, but notably one level below BSL-4. The controversy over this research has never fully died down. In 2014, after several high-profile lab accidents involving anthrax and smallpox at U.S. government facilities, the Obama administration imposed a moratorium on gain-of-function research, experiments that make pathogens more dangerous. The moratorium specifically covered research that could make influenza, MERS, and SARS viruses more transmissible or deadly. The moratorium was lifted in 2017 under new guidelines, and gain-of-function research resumed. The debate continues. Is this research reckless, creating pandemic pathogens that wouldn't exist in nature, or is it necessary to understand and prepare for naturally emerging pandemic threats? Meanwhile, the engineered H5N1 strains exist. They're stored in freezers. They've been shared between research labs. Every facility that has samples is a potential point of release. And unlike natural H5N1, which doesn't spread easily between humans, these strains were specifically engineered to do exactly that. Original SARS. The original SARS, severe acute respiratory syndrome, coronavirus emerged in 2003, causing a pandemic that infected over 8,000 people and killed 774. The virus spread internationally, reaching 29 countries before being contained through aggressive public health measures. SARS had a fatality rate around 10%, much higher than seasonal flu or even COVID-19. After the pandemic was contained, SARS disappeared from nature. The last human case was in 2004. Like smallpox before it, SARS was eliminated, not through vaccines, but through old-fashioned quarantine and isolation. And like smallpox, we kept it. Samples of SARS-CoV are stored at multiple BSL-3 and BSL-4 facilities worldwide. Here's where things get concerning. After SARS was eliminated from nature, there were multiple lab escapes. In 2003-2004, there were 4 separate incidents where SARS escaped from labs. In Singapore, a graduate student became infected through a lab accident and spread the virus to others before being quarantined. In Taiwan, a SARS researcher became infected in December 2003, potentially exposing 74 people on an airplane. In Beijing, China, in April 2004, 2 researchers became infected in a lab studying SARS. They spread the virus to others, causing a small outbreak. 1 person died. The outbreak included a 20-year-old nurse who had no connection to the lab, pure secondary transmission from a lab escape. These weren't theoretical risks. SARS actually escaped from labs multiple times after it was eliminated from nature. The virus that no longer existed in the wild was brought back through lab accidents. SARS samples are stored at facilities including the CDC, various Chinese research institutes, Canadian labs, and European research centers. The justification is research, developing vaccines and treatments in case SARS re-emerges, and studying coronavirus biology to prepare for future pandemics. After COVID-19, research on SARS-CoV has increased because understanding the original SARS helps understand SARS-CoV-2. But SARS-CoV is uniquely concerning because we know it escapes from labs. It has a documented history of doing exactly what we fear, getting out of containment and causing outbreaks. Each facility storing SARS is a potential source of a new SARS pandemic. Moreover, research on SARS has included gain-of-function experiments. Scientists have created chimeric SARS viruses, combining parts of SARS with parts of other coronaviruses to study how different viral components affect transmissibility and virulence. Some of this research has created viruses that don't exist in nature and are potentially more dangerous than the original SARS. The COVID-19 pandemic has sparked intense debate about the origins of SARS-CoV-2. While most scientists believe it emerged naturally, the lab leak theory that SARS-CoV-2 accidentally escaped from a research facility has received serious consideration. Whether or not COVID-19 came from a lab, the debate has highlighted that coronaviruses are studied extensively in labs, and those labs are potential sources of outbreaks. SARS-CoV samples exist in freezers around the world right now. The virus that naturally went extinct is being kept alive artificially for research, and we know from documented history that it can escape. Every day those samples exist is a day we risk bringing back a disease we already eliminated once. Monkeypox. Monkeypox became globally notorious in 2022 when it spread internationally, causing the largest monkeypox outbreak ever recorded outside Africa. The virus is a relative of smallpox, though typically much less deadly. However, monkeypox research in labs has involved creating more virulent strains and studying how closely related pox viruses can be manipulated. The concerning aspect isn't monkeypox itself, it's the research being done on pox viruses in general. Multiple labs study orthopox viruses, the family including smallpox, monkeypox, cowpox, and others, to understand how these viruses work and to develop broad-spectrum treatments. This research sometimes involves creating hybrid or modified pox viruses. In 2017, researchers demonstrated that they could synthesize horsepox virus from scratch using mail-order DNA fragments and published genetic sequences. Horsepox is closely related to smallpox, The researchers argued this was important to demonstrate that smallpox could potentially be recreated by terrorists or rogue nations. Therefore, we need better defenses. Critics argued they'd just published a recipe for bioterrorism. The same techniques used to synthesize horsepox could theoretically be used to synthesize smallpox or to create hybrid pox viruses combining the transmissibility of one strain with the lethality of another. Research has also explored what genetic changes would make pox viruses more virulent or more resistant to vaccines. Samples of various orthopox viruses are stored at BSL-3 and BSL-4 facilities worldwide. Research intensified after the 2022 monkeypox outbreak, with scientists studying why this outbreak spread so differently from previous outbreaks. Some research involves manipulating monkeypox to understand its transmission dynamics, essentially making it more transmissible in lab animals to study how transmission works. The risk is that research intended to understand pox viruses could create new, dangerous variants. A modified monkeypox strain that combined easy human-to-human transmission with smallpox-level lethality would be catastrophic. And the 2017 horsepox synthesis demonstrated that the technology exists to create pox viruses from scratch, meaning even if all samples were destroyed, the information exists to recreate them. Monkeypox itself has a relatively low fatality rate, 1 to 10%, depending on the strain and access to healthcare, but it's painful, disfiguring, and can cause severe complications. A more virulent strain escaping from a lab could cause a pandemic worse than the 2022 outbreak. And research creating more dangerous strains, even for legitimate scientific purposes, creates samples that shouldn't exist. Reconstructed extinct pathogens. Beyond the specific viruses already mentioned, there's a broader category of concern: extinct pathogens that have been or could be reconstructed. Scientists have developed the capability to reconstruct viruses from historical tissue samples, or even just from published genetic sequences. This means viruses that disappeared from nature, either through eradication or natural extinction, can be brought back. The 1918 flu reconstruction proved this was possible. But other extinct pathogens could be reconstructed. Ancient diseases preserved in permafrost or ice cores, including viruses that infected humans thousands of years ago. Historical pathogens like medieval plague strains, which have been partially reconstructed from DNA extracted from plague victims' teeth. Extinct animal viruses that could potentially jump to humans if reconstructed. Research facilities studying ancient DNA and paleomicrobiology are reconstructing genetic sequences from extinct microorganisms. While most of this research focuses on bacteria and doesn't involve creating live pathogens, the capability exists to synthesize live viruses from ancient genetic material. In 2016, researchers reconstructed a 30,000-year-old virus from Siberian permafrost. They revived the virus, which infected amoebas, not humans, and showed it was still infectious. This demonstrated that ancient viruses can remain viable or be reconstructed even after millennia. As climate change melts permafrost, there are concerns that ancient pathogens could be released naturally, but labs are also deliberately finding and studying these pathogens. The philosophical question is, should we be bringing back extinct viruses at all? These pathogens went extinct for a reason. Either we eliminated them or they died out naturally. Reconstructing them creates risks that didn't previously exist. Yet every reconstructed virus is stored in a lab, creating a potential point of release. Some of these reconstructed pathogens exist at facilities including the CDC, NIH, various universities, and international research centers. The justification is always research, understanding disease history, preparing for similar pathogens, developing broad-spectrum treatments. But each reconstruction is a Jurassic Park moment. Just because we can bring something back doesn't mean we should. These 10 viruses and virus categories represent some of the most dangerous pathogens stored in laboratories worldwide. They exist in freezers, secured behind multiple containment barriers, monitored by security systems, accessible only to authorized personnel. They're kept for legitimate reasons: research, vaccine development, public health preparedness. But they represent an existential risk. The fundamental question is whether the benefits of keeping these pathogens justify the risks. Proponents argue that we need to study deadly viruses to develop countermeasures. How can we create vaccines without samples of the virus? How can we prepare for future outbreaks without understanding past pandemics? How can we defend against bioterrorism without studying potential bioweapons? Critics argue that the risks are too high. Every facility storing these pathogens is a potential source of release. Lab accidents happen. We've documented escapes of SARS, anthrax, smallpox scares, and numerous other incidents. Security can be breached. Employees can become disgruntled. Natural disasters can damage facilities. Human error is inevitable given enough time and enough facilities. The COVID-19 pandemic, regardless of its origins, demonstrated how devastating a respiratory virus can be, even with relatively low mortality, around 1%. Now, imagine a virus with 50% mortality like H5N1, or 70% mortality like Ebola, or 90% mortality like Marburg in some outbreaks. Imagine these viruses spreading with the efficiency of influenza or SARS-CoV-2. The death toll could be in the billions. Some of these viruses, smallpox, SARS, the 1918 flu, were extinct or eliminated. They didn't exist in nature. We chose to keep them or bring them back. That choice creates ongoing risk. Other viruses, Ebola, Lassa, Nipah, exist in nature and will cause outbreaks regardless of whether we store them in labs. But concentrating them in high-security facilities creates the risk of larger releases than would occur naturally. The engineered viruses, modified H5N1, hybrid pox viruses, reconstructed extinct pathogens, are particularly concerning because they wouldn't exist without deliberate human creation. These are viruses designed to be more transmissible or virulent than natural strains. They exist solely because scientists created them for research. If they escape, will have caused the very pandemic we were trying to prevent. Regulation of these facilities is inconsistent internationally. While the US, Europe, and other developed regions have strict biosafety protocols, enforcement varies. Facilities in some countries operate with less oversight. The more facilities storing these pathogens, and the more varied the security standards, the higher the aggregate risk. There have been calls to destroy all remaining smallpox samples for decades. The WHO has repeatedly voted on the issue, and repeatedly the decision has been to postpone destruction. Similar debates exist around SARS samples and other eliminated pathogens. The research community generally opposes destruction, arguing we might need the samples in the future, but might need is weighed against might cause a pandemic. The COVID-19 pandemic should be a wake-up call about lab biosafety. Whether or not SARS-CoV-2 came from a lab, the pandemic exposed how unprepared the world is for a serious outbreak. Now consider that labs around the world are storing viruses far deadlier than COVID-19, and sometimes creating new, more dangerous strains for research. Some experts have proposed alternatives to storing live pathogens. Instead of keeping viral samples, labs could store just genetic sequences. Modern synthetic biology allows creating viruses from genetic sequences relatively quickly if samples are truly needed. This would eliminate the risk of accidental release while maintaining the ability to work with viruses if necessary. But this approach has its own risks. It might make it easier for bad actors to create bioweapons from published sequences. Others have proposed reducing the number of facilities storing the most dangerous pathogens. If only 1 or 2 maximum security facilities globally stored smallpox instead of 2, the risk would be halved. If only a handful of facilities stored Ebola instead of dozens, the aggregate risk decreases. But centralization creates other problems. If those few facilities have problems, the entire world's research capability is impacted. The uncomfortable truth is that there are no perfect answers. Storing these viruses creates risks. Destroying them eliminates research capabilities that might be needed. Reducing the number of storage sites concentrates risk, but also makes security easier. Publishing research helps the global scientific community, but also provides information to potential bad actors. What's certain is that right now, today, civilization-ending viruses are stored in labs around the world. They exist in quantities sufficient to cause pandemics. They're secured by human systems that will inevitably fail given enough time. Some of them have already escaped from labs historically. and research continues to create new, potentially more dangerous strains. Every day those viruses remain in storage is a day we accept the risk that they might escape. Every new facility that stores them increases the aggregate risk. Every gain-of-function experiment that makes pathogens more dangerous creates something that shouldn't exist. The question isn't whether a lab release will happen. The question is when, and whether we'll be prepared for it when it does.